Okay, let's start lesson. So let me share my screen. And now we'll continue the exercise session 1. So here we have examples to loss of significant digits, rounding numbers, and finding relative errors. So we started exercise number 2 and considered first and second functions, I think. And here the condition to this example is it's given x and n number, and from 1 till 16, and x 10 to the power of minus n, and we have this function f3, for example. And now reformulate this kind of function in order to avoid loss of significant digits, and assuming the values obtained using reformulate function as exact values, and then compute relative errors and compare with machine precision. So then print the result of relative error for every x, corresponding x, and then sketch the graph, graphically represent this kind of function. So here we have this kind of function, for example, and how to reformulate this function. How to reformulate this function. Reformulate, it means we need to change to new function which is algebraically equal to this function, but when we do machine operation, so here we have some kind of errors. They are same algebraically, yeah, but they are equal algebra, but they are not same in machine operations. So let's begin with this example. Okay, let's use here format long E. Format long E. So we can use here format any other formats also, but when we use format long E, it will be more digits after 0. So we have 16 digits here. However, we have here n from 1 till 16. You can see it's x to power of 10 to power of minus till 10 to power of minus 16. So we need these numbers. We need these digits. And that's why we'll use format long E here. And now you can see n from 1 till 16 and x is 10 to the power of minus n. Just give these values. N is from 1 till 16 and x is 10 to the power of minus n. So here we will use here vector power, because of now x is vector. And now let's write here f3 now. So f3 here is 1 minus square root of 1 minus x squared. f3 is equals to 1 minus, in break now sqrt will denote square root. So sqrt will give square root with sqrt common. 1 minus x squared. This is clear? So now let's change the function f3, new function here, for example. How can we change here this function? Reformulate this function. We need to use alternative function to this function. What will be here? Can you answer to this question?
Yes, Professor, maybe we may just write x squared divided by 1 plus square root of 1 minus x squared.
Yes, of course, because we just multiplied and divided by conjugation form to this expression. Yeah, however, we have irrational expression here, and we can do this. If you remember, we can do rational in denominator. Yeah, if we have, for example, in denominator irrational expression, we just multiply it by conjugation one to be used for formula a square minus b square and get the rational expression. So here also we can do the same work. Correct. So in this case, it will be, let me write here. So in this case, it will be just 1 minus sqrt 1 minus x squared. So we need to multiply by and divide the same one, but in the middle we have just plus. In the middle we have plus. And here dot division. To this one. Yeah. So, and now when we open the brackets, when we multiply numerators, so here we get just after simplifying, the 1 and 1 canceled, and it will be just x squared and dot division here. Or we can do without brackets here. And here brackets we'll put, and our expression is plus. So here also plus we have. Now this expression we get new function. Yeah, it's algebraically equal to this function, but we reformulated given form. Okay, now just copy this one and put here. Okay, so let's continue now. And now let's find the error between them. So just denote by ER3, for example. And how can we find error? So this is difference, absolute value of difference between f3 and the new function f3 underline. We need to find it with respect to new reformulated function. Reformulated function, it will be now as exact value function and divide by absolute value of f3 underline. So ABC f3 minus f3 underline divide by ABC f3 underline. So now let's show the result as table. So to do it, we need to use these square brackets, and here, for example, the values of x to be compared, and values of f3. You can add f3 new one also, or just we need errors here, ER3. So it will be now as columns will get the result here. And you can see here this kind of corresponding values here, the values of x, the left side, in the first column. So from -1 till -16. And here the corresponding value is for F3. And here corresponding value is for error. You can see beginning from for nines place, it will be just zeros. So in our format. So that's why here we have just ones. Because of it's very small numbers.
I'm sorry, Professor, I have a question.
Mm-hmm.
Why do we use ABC when we write like error?
So this is absolute value.
Oh,
Error.
absolutely. Okay.
Is it clear? So
Yes,
error.
yes. Yeah, now I understand. Okay.
Understand? Yeah,
Thank you.
fx minus f, for example, x. This kind of f. It's approximated. Yeah, new one, for example, and over, for example, if it's with respect to given one fx, for example, like this.
Okay, thank you.
Mm-hmm. Not at all. So now we have a result, and now we need to graphically represent it. Right. So you can see here this number is very close to machine precision. Of minus 16, 2.2 times 10 to the power of minus 16. We have 16 digits. So this number is very close to machine precision. And here you can see this one is also close to the machine precision. Okay, now let's sketch the graph here. So to sketch the graph, logically, we will use now what kind of command? Log. Because of here we have as x numbers with tens powers. And it will be useful to use command log, logarithmic scale for both axes. So log. And in this exercise, we will consider also a logarithmic scale for one axis, for example, for y-axis. It's possible also. So here log just for both axes, and ex first variable and second variable er3, and you can give any color here, and line widths. So now just enter, and here we have our graph. You can see this kind of graph. So here we have as x-axis numbers with 10 to the power of minus n, beginning from 1 till 16. Yeah, and here we have relative errors. So this is axis for relative errors.
Can we say that we use log when we have very small numbers?
Yeah.
Okay.
Yeah. When we have 10 numbers with base 10, it's very useful. When we have numbers with base 10, this is useful command. When you use plot, for example, you cannot get such kind of graph because of they are very small numbers. You said they are very small numbers. So if you use plot, it's just normal scale. So, and in this case, you can see just like this, because so here from 0 till 0.1 it takes. Here also from 0 till 1.2 it takes. So here scale is very large in this case.
Oh,
To
yes,
represent this kind of graph.
yeah.
But our numbers is very small. Okay?
Okay, yes, I understand.
Good. Now, let's continue. If it's clear. So let's do now F4. So the same work. So here it's very easy. We just need to open the brackets in this case. And it's equals to what we have here. If you open x squared plus 2x minus 1, yeah, x squared plus 2x minus 1, plus 1, sorry, plus 1 and minus 1 here. They are cancelled over x here, yeah. So, and it's equals to just x 2. So here we have 2x, x squared plus 2x, yeah? X squared plus 2x over x. So it will be just x plus 2. However, x not equal to 0 here. We can divide, yeah?
Yeah.
So just x plus 2 we have. And now let's write it in Matlab operation. So here we have again our given values. So now you can write f4 was equals to x minus 1 squared, x plus 1 here too. X plus 1 squared minus 1 and over x. So it was given function, and now new function f4 underline. Here we have just x plus 2. And now let's find again relative error between them. So when we reformulate our function, we have relative errors between them. So not this one. Here f4 corresponding functions, f4, and here error 4. And now let's show the result here. ER4 and F4. Now you can see here the result. Is it clear?
Yes.
Again, same. Here we have x, here we have corresponding functions for F4 and the corresponding relative errors. You can see the relative error here also increased. So this one is very close to when x equals to 10 to the power of minus 2. So 0.01, yeah? It's really close to machine precision. You can see here. So it means here, if x equals to 10 to power of minus 2, it's acceptable, this relative error, because of it's very close to machine precision. And you can say the first one also. But for others, it is greater than machine precision. Do you understand me?
Okay, yes, Professor.
Good. Now, again, just show the graph here using log. Here we have ER4 now. Let us show it. So here you can see the new graph.
Okay.
Now, let's continue. So can I clear all?
Yes, yes.
To save for yourself it? Okay, now let's continue. Now, next exercise. consider the sequence, number 3, consider the sequence x. So we have this kind of sequence, and this sequence is, it gives us pi approximation. So we considered in lecture also this kind of sequence. So the first value is 2, and the x n from beginning from 2, we can define by this way. And this is very close to number pi. That's why it's called pi approximation. And now we need to compute relative, but it's not pi. It's pi approximation. That's why we have here errors, some kind of, and compute the relative errors between them, pi and with respect to pi, and consider n equals to 40, from 1 to 40, and plot the relative errors here using logarithmic scale. After that, we need to find new x, reformulated x here, x and tilde, which is equivalent to x, which avoids loss of significant digits, and graphically represent errors between now new reformulated xn with pi. So now let's begin. So here we have now, however, we have n from 1 till 40. We need to enter vectors here, and the size of this vector should be 40. Now, let's enter vectors. As starting values vector, we will consider 0 vector of zeros, 0. And here we have how many rows? M rows, 1 column. We'll change M from 1 till 40 with loop. Okay, now let's continue. And we have the first value. So it is 2. X1 is 2. And now open loop for n from 2 till m. Because we have first value, we wrote it. Now we need to write just beginning from the second one in this general sequence. And let's give this xn. Give this xn. It was 2 to the power of minus 2 to the power of n minus 1 over 2, and this expression. Okay, so let me type it. So 2 to the power n minus 1 over 2 times sqrt, and now 1 minus sqrt, 1 minus, it was 4 to power of 1 minus n. In this case, this is not vector because here we use a loop, yeah? For each n, we have corresponding values we get just. That's why we put just this power without dot. Do you understand why without dot here?
A little bit. Can you explain again?
So in previous examples, it was vector. And for each vector, we have the open values. But in this case, this is also vector. But in this case, we open this loop cycle. And here we have one value only. For example, for n is 2. First of all, put here 2 and compute it. And then 3 and compute it. Separately.
Oh, okay. Yes, now I understand.
Yeah.
Okay, thank you, Professor.
Okay, now this is, let's continue. So it was xn minus 1 squared. Okay. Now, just this one, and multiply by xn minus 1. We'll write it like this, xn minus 1 and squared. Okay, and just close the loop. And now find relative error, ER. So it's equals to now absolute value of number pi. We can do with pi, just write pi. And the pi minus x, just division here also, and absolute value of pi. With respect to pi, it should be find relative error. And now use logarithmic scale to draw the graph. And here I said we can use only for half of axis, for example, for x or y axis. In this case, x axis is from 1 till 40 just, yeah. And but y axis, this is error axis, and here it will be little very small numbers. That's why we just use for y axis logarithmic scale. And how to write it? We have the next command, semi-log y. So it means just half of logarithmic scale and plot using logarithmic scale for y-axis, only for y-axis. Is it clear?
Yes.
Not log, semi-log y.
Okay, yes.
And you can do same work with x-axis also, semi-log x it will be just. Okay, now it will be from 1 till m. This is x-axis. Y-axis is relative error, ER. And you can give color any. And line widths. So now let's check it. So we can see here our plot using this half logarithmic scale, semi-log y. You can see from 0 till 40 change. Here we cannot do logarithmic scale. However, it will be very small in logarithmic scale, but they should be bigger number. Yeah, more big numbers here from 0 till 40, from 1 till 40 in this case. And you can see on the left side, this is logarithmic scale for y-axis here, and this is a relative error, corresponding relative errors. If we want to change just with log, you can see difference between them. You can see difference between them. So here it's continuous just 40. Here it is 40.
Oh, okay. I'm sorry, Professor. So how can I define from the problem what should I use, log or semi-log y?
So I said here you can see for x-axis it is from 1 till 40, and you can use here normal scale from 1 till 40. But for y-axis, they are very small number. That's why we need to we have to use the logarithmic scale here.
Oh yes, I got it. Okay, thank you. Yes,
if
because
it is normal numbers, if it is, for example, not numbers with 10 bases, so you can use just plot, for example, here.
Okay, thanks.
And now let's continue. Now we should reformulate our function. And how to reformulate this function? Find alternative form for xn here. So here also we can use as this example, just multiplying conjugation form and divide by it, yeah? Here. Inside. Do you understand me?
Yes, just
Just
write like
multiply
for
and
Matlab.
divide by it.
Yes.
Yeah. Now just try to write the expression for it. So again, m is 40, and we have x vector. We have starting value here, and let open again loop and write the new one now. Xn now equals to, now I will write here the ready one, and then we'll explain xn minus 1. We did with previous groups also. So sqrt here, now it's instead of 2 over, in the denominator will be here plus 1 plus sqrt in the middle. Conjugation form it is, and 1 minus, without changing here, 1 minus 4 to power of n, 1 minus n, 1 minus n, and times here xn minus 1, xn minus 1 squared it was. Yeah, so you can see here 2 over this one. This is conjugation form for our this one. Is it clear?
Yes, Professor.
You can prove it. Okay, now let's continue. Put semicolon. If you don't put semicolon, it will show to us result, but we don't need the result here. And close the loop. Okay, now error. Let's denote by error 1, and let's write ready one. Error 1, for example, and here again we will use now semi-log y to graphically represent this function. Let's do black. And you can see the graph of this function here. This kind of graph we'll get.
Okay.
Okay?
Yes. I understand.
Good. Sorry, let me check one more time this function. Xn minus 1 here, it should be sqrt 2 over. Sorry. We have some kind of mistakes here. Because of graph was another, so here we miss
Yes,
it.
I was like it was a different way.
Here we miss it parentheses, so sorry. Here we miss it parentheses, that's why. So let's open one more time loop. One plus sqrt 1 minus 4, 1 minus n, xn minus 1, xn minus 1, yeah, and power 2. Now I think it's correct. Sorry, so one more parenthesis. Yes, of course. Matlab remind us one more parenthesis here. Parse error. So end. Just a second. So I think it was correct. Let's just type it one more time. M40. Here x is 0 vector, and we have here first starting value of x, and now open loop, write new function. So xn equals to xn minus 1 sqrt 2 over 1 plus sqrt 1 minus 4 1 minus n 2. Now it's correct. And now it's working. So now find relative error here. And what should you do? Find the graph. Draw the graph here. Semi-log y. Where is our semi-log y? So this one. Let's do it. Just a second. So, and this one is correct graph. Here you can see another graph. So we just missed our one parenthesis. So that's why we have another graph. Is it clear now?
Yes. Okay.
Okay. Let's continue now and do next exercise here. So given the function f of x is equals to sine x, and approximate this derivative of x using the following difference quadrant. You know from mathematical analysis course, definition of derivative, yeah? It was fx plus delta x minus fx over delta x as limit tends, delta x tends to 0, yeah? It was equal to derivative of the function f prime, yeah? Do you remember?
Yes,
This formula?
probably. Yeah, I do remember.
Yeah, so now just we need to approximate this function with this expression. The given function, it is sine x, and you can see that you can do h or delta x, they are tends to 0. And here you can see the alternative form for derivative. So we just compare our derivative of f. Derivative of f here just cosine x, yeah? Derivative of sine. Cosine x with rx.
Yes.
Is it clear?
Yes.
So we have this definition. This is equal as h tends to 0. But they are algebraically equal, but not same functions. So now just we approximate, they are approximated functions. That's why we will just compare this cosine x with r. And we have given h and k. And fix, for instance, x. We just fix it and graphically represent this relative error. And after that, reformulate this rx. So again, we need to find another form of rx to avoid loss of significant digits and graphically represent the new relative error. The same work. Okay, now just right here. So let us first of all begin with the value of x. We fix it. It is pi over 4. And now k here from 1 till 50, and h here 2 to the power of minus k. So k from 1 till 50, and h is equals to 2 to the power of minus k, and here we need to put dot minus k. Okay, and now just write the r. R, it's here sine x plus h and minus sine x. Sine x, and here over h. Find relative error now, ER. So absolute value of, now just instead of f derivative, we'll write cosine x. Cosine x and minus r. And then divide by absolute value of cosine with respect to exact value. Absolute value of cosine x. Okay, now find the graphical represent it. So log. Now log we will use because of you can see here for h will be now first variable. H, it's very small number here, 2 to the power of till 2 to the power of minus 50.
Yeah.
H error any color. Let's do any other color, magenta. So then line width is 2. Let's check it. And you can see such kind of graph we have. Let's show it as table. So here h value and r function corresponding and the error. And you can see here how many. However, h is from 1 till 50. So if 2 to the power of minus 1, it is 1 over 2, 0 0.5, etc. You can see 50 rows here, and corresponding values for h, r function, and the error, relative errors.
Okay. Yes.
And here we have graph for these values. Here we have h axis, and this one is error.
Okay.
Okay, now let's continue. And we need to reformulate our function. And to reformulate our function, what should we do here? Here, just use trigonometric identities, trigonometric formulas. Just sine alpha minus sine beta. Use this formula.
Yes.
And it will be when we use it. So let me write here. It's equals to it will be 2 times it was in before minus, and with 2 minus will be plus sine h over 2 x sine alpha minus beta h over 2 and then dot multiplication, of course, cosine alpha plus beta, cosine and alpha plus beta will be 2x plus h over 2, or x when we divide by 2, x plus h over 2. And over dot over, here we have h. Is it clear?
I'm sorry, Professor, how did you get this result?
We used sine alpha minus sine beta, sum to product.
There is like the formula, yes, for this equation.
We just changed our numerator using this formula. Yes, sine alpha minus sine beta.
Okay, yes, now I understand. Yeah.
Yeah, this difference to product, or sum to product, you can say. So it was if it is minus here, sine alpha minus beta, it was so here you can see x plus h. It was 2 times sine alpha alpha minus beta over 2, and the cosine alpha plus beta over 2.
Yes. Yeah, now I understand.
Is it clear now?
Yes.
Okay, let's continue. And here use this formula. Now new R2 function, it was equal to this function now. And here error, we need to find again error 2, for example, and here now R2. Yeah. So let's now use logarithmic scale to build our function. Let's do green, for example. You can see it's just straight line. It will be strictly increased function.
Okay.
This straight line. Is it clear how to use this approximation, finding relative errors, loss of significant digits?
Yes. Yes. Thank you, Professor.
Any questions?
I have one question, Professor. From the previous problem, you used like the cosine. I have a question. How did you get cosine when the equation says that we have only sines?
Yeah, cosine, this is just exact value of derivative f of x. However, f of x is sine, and we need to compare with f derivative of x. F derivative of x, it is cosine x.
Okay, yes, now I understand.
That's why we just use it instead of f derivative. Here you can see the formula, yeah? F derivative of x minus Rx any.
Yeah, and then you just substitute it.
Yeah, just substitute f derivative is cosine.
Okay, all right. Okay,
this is just as exact value for derivative.
Okay.
Exact value minus approximated value. Okay, any other questions?
No, thank you, Professor.
If you don't have any questions, we can finish today's practice. It was the last example for today. And the next time we'll continue and we'll start new session 2.
Okay,
Thank you for attention.
Thank you.
Thank you. Goodbye.